if I had to pick one skill that I would work on over and over and over again for you, it would be session hijacking. This requires an interaction between two hosts and inserting yourself into their communication path. That means you either need to be really close to the source or the destination. If you have that proximity and you can take over an authenticated session, you win. You've gotten past the normal authentication controls, and you can dig much deeper in at that moment in time. What you're saying in session hijacking is, I will let somebody do all the heavy lifting of setting up the session, doing the authentication, and going to the resource that they need, and then I'll take over. And that's what session hijacking does for you. At what layer? Well, it depends. There is session hijacking at all different layers. Certified Ethical Hacker talks about session hijacking lower, like TCP and IP, right in that area. But I think that we need to go beyond that and start looking at the application layer, the HTTP of it. In session hijacking, we're definitely gaining access. We're getting a hold of a live session, a communication, and we're inserting ourselves into it. So that's really where we are. There are different layers of hijacking. We're going to look at the two important layers, one for the exam, but also the other for your capability to learn and grow as a penetration tester. Before we do that, unfortunately, we have to do a little bit of TCP/IP version 4. And so we're going to get into the technicalness of it. And remember, at the very beginning, I gave you a pretest and I said you have to understand TCP/IP concepts and ISO concepts. If you don't know the OSI model, this is going to be a little tough on you. So if you feel a little lost in these areas, I'm going to give you lots and lots of resources from what I do to learn, and you're going to have to take that extra time there. If you want to be skilled in this area, you're going to have to work a little harder than normal. Now, we're going to talk about there's a difference between spoofing and hijacking, and that causes a lot of problems. So we're going to delineate those two. We'll talk about the types of session hijacking and a little bit of sequence prediction. Okay, for the exam, you're going to have to know your protocol headers. Now, this fits back into the sniffing section. If you're looking at Wireshark, you know what your protocol headers look like. And also, what that does for you is that stops a lot of the wrong answers, all the crappy answers that you go, well, that's not the truth because they flipped those two bits there. It cuts those things away. And you're also going to have to know the format of your attacks. We're going to do both session hijacking layers, both TCP/IP and application HTTP session hijacking. Okay, so prerequisites: headers, layers, concepts, flow of the message packets, understanding TCP/IP stack, spoofing attack, and hijacking attack. Now, the two last pieces down here. Spoofing attack is impersonating. That is pretending to be you. I do not have any credentials. I just say, hi, I'm the President of the United States. And you go, okay. Hijacking is the President of the United States came along, introduced himself, and I bumped him out of the way and I said, hi. I want to take over this conversation. In the spoofing, we may or may not have authentication. In the hijacking, somebody did the authentication for us. When we look at the IPv4 header, this is it. This is a block diagram of it, starting off with version. Now, version at the 0 bit basically is 4 most of the time. What you will see in the very beginning of all IPv4 packets is 4500. If it was a v6 packet, it would be start with a 6 for version 6. Type of service, total length, identification, flags, those IP flags, fragment offsets, time to lives. All of these tools here, we're going to manipulate some of this in our session hijacking. remember there's a data field. So let's back up for a second. Notice at the bottom you don't see where it says data, but after options and padding is data. This data field is carried to the next layer. In de-encapsulation, at IP layer, I get this and I say, okay, all these things have been satisfied and I can set up all this communication with you here, and there's a piece of data inside of here. You've satisfied that. I know I want to send it up the stack. I don't know what this data is, but I'll pass it up to the next layer. I don't care what it is. You satisfied my requirements here. That's important to understand, that when we de-encapsulate at this layer, we don't care. If I can get you to satisfy the requirements at one layer and be different in another layer, the abstraction between the two layers, I can take advantage of that. In IP, it's unauthenticated traffic. In TCP, it's authenticated traffic, but only at session. So, in TCP IP, we've got a header concept. There's abstraction from one layer to the other. In TCP layer, we do sessions and stream. In IP layer, we do transmission, and those layers separated. What we do is we take advantage of the difference between these. I could literally jump into your IP TCP conversation with a different IP address and the same stream. If you set up your sequencing up here at this layer and your IP addresses are down here at this layer, if I can figure out what the sequence is, I can be wrong about the IP address and right about the sequencing and take over the session. The tool to do this with is called Hping. Okay, so here's your TCP header. It's got its own set of flags inside of it. The sequence number and the acknowledgement number is the thing that you want to predict and take over with a different IP address. That is a classic hijacking technique. So this is the TCP header. You need to have a clear understanding of both of these in order to make session hijacking work well. When we talk about connections and connection control, we need to separate out connectionless data transfer from connection-oriented data transfer. Remember, each protocol data unit is treated independently and connectionless. HTTP is connectionless. So each individual protocol data unit, at that point it's called data, is treated by itself as a whole. And so the authentication needs to be inside of there in some way, shape, or form. When we look down the layers and we go to IP, the authentication needs to be within that particular packet before we de-encapsulate. And in IP, it's not. In connection-oriented data transfer, we create this virtual circuit, and to disturb that virtual circuit, we need to predict where the conversation is going. That's what we do when we do hijacking at the TCP layer. We look at the session variables and pass that data back and forth and get inside of that passing back and forth as those variables increment. That's your sequence number. If we can predict that sequence number in a connection-oriented data transfer, we can take over. We want connection-oriented from a security standpoint. We also want it for lengthy data exchanges. Connectionless requires that somewhere up above this level that we have authentication, or that each individual protocol data unit is in fact authenticated. And that's very difficult to do without a lot of overhead and a lot of management. Okay, so now let's talk connection control. If the protocol details must be worked out dynamically, okay, fine, we can agree with that connection control. There's a logical association or a connection established between the two entities. If we can break the logic in that, again, we can take control. So let's talk about the phases of occurrence. So connection establishment, data transfer, connection termination. Connection establishment, SYN, SYN-ACK, ACK, data transfers, bunches of SYNs and ACKs going back and forth, the sequence numbers incrementing. At the very end, FIN, ACK, there, we're done. And that's the example from TCP. It can be interrupted and we can restart that. And there is a recovery phase where we can handle errors. Suppose along the way that one of the hosts on either end gets busy. Instead of doing the acknowledgement of the next packet and saying, okay, give me 1,000 more, it can say, give me 500 more because I'm kind of busy. Give me 250 more because I'm busier. Give me 1 more because I'm really, really busy. Give me 0 more and wait because I'm really, really busy. So here's your phases of your connection oriented. Connection request, connection accepted. Okay, that's that SYNAC. Data exchange and the acknowledgments as we go along, multiple exchanges, and then the termination of it. Let's look at connection establishment. So each entity agrees to exchange the data. They've got the underlying communication, and now we're up in the TCP layer. One station issues the connection request. That's usually the client side of things saying, hey, I'd like to talk to you. And then the receiving entity says, I'll accept this request whatsoever. Most of the time, servers automatically accept. There could be a negotiation in there, especially when we're going to an upper layer protocol like an SSL protocol. We'll negotiate some other variables. It may be, okay, this is our speed, this is our data, this is our encryption algorithm, this is how we do that. We'll do some sort of syntax, semantics, and timing, getting us ready to go. Now the rule is that both entities have to use the same protocol. So if there's a difference in the versions of the protocol, we need to have backward compatibility. The perfect example of this is when we're talking about SSL connections and TLS connections. TLS is the newer version of the protocol, and if in our negotiations we go back and forth and you say, well, I only speak SSL version 1, and you speak TLS version 2, can you go slower? And we negotiate down. So sometimes what we can do is we can prey upon the fact that you will be backward compatible, or I will be backward compatible. Where this doesn't work is in instances where we're using something like IPsec. IPsec with a simplex connection says, no, if you can't communicate with this level of encryption and this level of rekeying, no, not at all. Now you're going to have options and features in there also, but usually this backward compatibility thing is the thing that we prey upon. Remember, we also agree upon the maximum size of the protocol data unit, how much data we're going to transfer. And some stations will restrict to lower octets. Data transfer and termination. So we both agreed on the data and the control information to exchange back and forth. We get that out of the way. We do the data flow and acknowledgments. We can do the acknowledgments in both directions. With TCP, that's exactly what we do. Some, like UDP protocol, since there's no connection set up, we just keep on sending and praying that we'll actually get the response. One side can terminate the request. It doesn't have to be both sides. It can say, I want to do a reset. That's why when you're attacking a network, an intrusion detection system can come in and say, we're going to do a reset on that channel on both sides. They're sending one reset one way and one reset the other way. It's not, they're sending them to each of the stations on either end. So at the termination request, we can also step in and start working against our adversary. So I know we're kind of high level at this point. We're kind of, talking around the subject and we're not getting down into the meat of it. And you need to hang on with me a little bit here because we still need to talk a little bit of theory before we actually get into it. I'll give you a set of steps for hijacking. It'll work and you can play around with it, or you can just like run straight to HPing and start playing around with that and not understand what you're doing. If you do that, what's going to happen is you're not going to be able to make up a new attack. Because the old attacks, once the defenders figure it out, they're not going to work anymore. You need to be able to be creative about this. You need to think a little bit deeper than just, okay, well, I'll just use HPing. I mean, it's a great tool, don't get me wrong, and it works in a lot of cases. But think about the next version and the next version and the next version. So sequence numbers is kind of the next step in this. We want to know a counter that steps forward throughout our conversation to control that conversation. It also helps with the reassembly of that conversation if there's some fragmentation across the stream. We have no idea what the size is going to be. It's not predictable. The only time it was ever predictable was actually in ATM cells, and they were a fixed size. We don't do that with TCP IP. We say it's variable size and length. And with V6, we actually have what's called jumbo. So we go from standard packet size to jumbo packet size. But in all this, when we talk about sequencing, what we're saying is, what's the flow of data across this? And we, as the attacker, we want to successfully guess the sequencing and jump in at that area. Okay, so let's talk a little more about sequencing. Many connection-oriented protocols use sequencing. TCP uses it. Protocol data units are numbered sequentially, and they increment as they go along. What this does for us is it gives us ordered delivery so they can do reassembly quickly and efficiently, flow control so that we can respect the fact that there may be congestion, and error control in case a packet gets dropped. We have to include some way to identify that connection, a unique connection identifier. Usually what we do is the pairing of the IP address with the port number and the sequence number. All of that together gives us a predictability. That's identifying that connection. But remember, those are all at different layers, so we can start playing with the game there. So the attacker, when they're looking at the sequence numbers, they either have to know it, so it starts. Let's say, for argument's sake, that you're non-random and your server initiates. The Windows NT4 server prior to Service Pack 3, prior to Service Pack 2, I think, actually started with a particular sequence number. It was always starting at this number. So if you could reset the connection, you could know, okay, the first piece in that connection is going to be this sequence number, and you could jump into the stream. You could also force it to be known. You could advance it or slow it down in some way, shape, or form and say, I know that this is what's going to happen next. So you can force that to be known. And then finally, there's predicting within a range. You say, well, how would predicting in a range work? Well, what I could do is I could craft a whole bunch of packets. So let's say that I know that the range is going to be, for the next step in the sequence number, is going to be between 1 and 100. And there's like 100,000 after that. 1 to 100. I can create 100 packets. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 100. And I can send all of them to you at once. If I know that they're in this range and I know that's about to occur and I send all those packets out, if I hit it just right, I beat the other guy to the punch and I take over. That's very noisy. What we would like to do is we would like to know it, or we'd like it to force it to be known. In other words, force a particular number to occur. Not to send a spray of packets out there, because then we're going to get caught. Remember, spoofing is pretending to be another user or machine to gain access. You're not taking the other user offline. You're pretending to be somebody else at the packet level. Hijacking relies on the legitimate user to do the authentication and the connection and get all that set up, and then the attacker jumps into the stream. What we want to do is we want to do this after the upper layer authentication has occurred. So if somebody was HTTP authenticating up here and we could jump into the stream down here, we win because they've already authenticated for us and we're good. Now, one of the tools that you want to use is called EtherCap. I like that. HPing is another one of the tools out there. I can't remember which one of those is the best tool from an exam standpoint, so I would say use both. EtherCap, Linux-only tool, is actually, I won't say it's a Linux-only tool. I will say it's the best tool on Linux for doing what you need to do when you're taking advantage of this session. The configurations on this you need to take some time to learn how to configure this tool. It's not very straightforward in my opinion. Okay, so now here are the steps. So I've been torturing you all along, and now I'll go ahead and give you, it's all been stick, and now it's a little bit of carrot. So track or predict a connection. That means that you're listening. That's why we did the sniffing first. Desynchronize the connection. We can establish but not transmit. So what we do is we shrink the amount of data that's being transmitted down to 1 or 0. So if we can reduce it down to 0, we're ready to go. Force the ACK forward. We're going, okay, we're at 0 now, or we're at this number, and we're not moving forward. Now we're going to move one at a time, and we're going to keep on moving slowly, one at a time. And you agree, I agree, 1, 1, 1, 1, 1, or 0, 0, 0, 0, 0 in that session. We could reset and get a new sequence number, but usually what happens is that forces us to re-authenticate. And then the attacker injects or receives the data at that point. They can see what's in the stream. And this is when you're looking in Wireshark, you want to look down in that ASCII area so you can see what data is being transmitted. Now you have to be really quick. Now, if you talk about Mitnick, his attack was about predicting the receiving side of it. You don't need to know about the Mitnick attack. You need to know that there is a very famous attacker out there that social engineered people into giving him information. Okay, now, this is going to hurt a little bit, but we need to look at where we are in the session. What state are we in based upon the flag? So I wanted to get that out of the way up front. This diagram talks about the possible different active open sessions, knowing what's going to happen next. I don't expect you to memorize this here, but I want you to know that it does exist, and you have to say, okay, where are we in this process? And if you can figure out where we are in this process, you can know what's coming next. So have we received, we're listening at this point, have we received the SYN? Are we ready to send the SYN in the ACK? Where are we in the conversation? And go all along your diagram, and once you've figured out where you are in the session, or predict where you're going to be next in the session, then you can do decent hijacking. Now, there are two kinds of session hijacking. There's the active one where we inject, and there's the passive one where we record. In the active one, we take over and we corrupt the integrity. In the passive one, all we're doing is we're collecting all this data for the next time. We're going to compromise confidentiality either now or in the future. Okay, so which one are we doing? Are we doing hijacking or are we doing spoofing? Remember, hijacking relies on the legitimate user to connect and authenticate and then take over the session. Do you have authentication credentials, yes or no? Can you get them, yes or no? If you can get the authentication credentials, you don't need to do hijacking. You spoof. Spoofing, you're attacking to be, you're pretending to be the other person or the machine to gain access. You probably have some credentials. So that's hijacking and spoofing. The tools are EtherCap and HPing. So we've talked about the tools that you're going to use in session hijacking for TCP IP version 4. And now we need to switch over to application hijacking, getting up into the HTTP. Now before we go any further, I want to thank Stallings. He's a god of application hijacking and iDefense. A lot of the slides that you see here I've adapted from their presentations because they said it so much better than I did. I looked at my presentation and I went, God, that's so much better. And so I've taken what they've said and I understand what they've said, and hopefully between the three of us we can get application hijacking to you. So we need to talk session IDs and how they work, the security problems with session IDs and the abstractions that we get there. And what we're going to do is we're going to brute force those session IDs in most cases. And then I want to show you some examples of where people have failed. And we'll use those examples and say, you see here, this is what they did. Now some of these examples, they're nice and clean and neat, and other ones not so much. So let's talk web application logins. You go to eBay, give me my user ID and password. You go to Yahoo, give me my Yahoo ID and password. You go to Amazon, surprise, right? So in traditional brute forcing, what we do is we put in some user account and then key in a password. Has anybody seen what they've been doing lately with a lot of these web interfaces? They don't want to shut you out and lock out your account. What do to you? They slow you down. They put in the squiggly, slanty letters, the CAPTCHA, right? And so they say 3 bad login attempts, come back later, or 3 bad login attempts, we're going to make you do more work because you might be an automated bot. Why don't we allow somebody to do their authentication, get that out of the way, and then just take over through authentication. How can we do this with an application? Well, we have to understand the fact that there's no state to HTTP. And the authentication tool that we use in HTTP is a fiction of authentication, because HTTP is stateless. So it says from one to the next, there is no conversation going on. We have to artificially create that somehow. So how often does the user authenticate? Keying in username and password is at the beginning of the session, and that's it. But that's not really what the authentication is. What happens is the application is actually creating a token that represents our authentication. So we're going to maintain the state with a shared string, a token, or a secret that the user doesn't have to key in every single time, because that would be a pain in the butt. So what we do is we take the authentication data, username and password, and exchange it for a session ID. If you can figure out what that session ID is, if it is predictable in any way, shape, or form, you win. That's the trick. Okay, so we can do session replay if they don't change their session IDs, those tokens, every single time. Or we can do session hijacking, where if we know that that control has been set up between the client and server, we can insert ourselves. But that means that we have to redirect them through us. So if we go back to the original portion of this, and we can redirect, when we go back one module, we can say, let's redirect man in the middle, redirect that communication through us. If we can redirect it through us, we can see what that session state is and hijack that session. Now, the rule is that session IDs should be just as secure as username and passwords, and you're going to see some examples of it's not. The authentication data is sensitive and should be protected as such, and it's not. Session IDs and authentication credentials are equal. Now, if you don't believe me, look at the RFC 2964. Okay, so how do we get a session ID? Well, they're generated by the web server and the web application, and then they're transmitted back and forth either in cookies, URLs, or hidden fields. So that's how the session ID is created. I need to give you a fresh cookie. No, I need to give you a cookie refresher. Yeah, you need to understand what they are. Okay, so a cookie is something that's set to expire. That means it deletes after a certain time. What we should do if we're creating good apps is close the browser session and make sure that that cookie goes away. That's when we want it to go away if we're developers. Attackers, we want it to be persistent so that we can pick it back up and use it for something else and track that state. What we do in a lot of cases to make websites user-friendly is we give them a cookie that gives us data back about them so that we can reestablish all of those choices that they made when they came to the website. I like my background to be green. I like you to use this credit card. I like you to show me my list of favorite books first. Remember me. We create those options to make it more convenient for the shopping experience of the end user. You and I know that from an attacker standpoint, any of that remember me stuff stored on the user hard drive, if we can get at that, then we win. Okay. So here is RFC 2965 and the 7 parts of a cookie. Domain flag path, secure, fix, expiration, name, and value. The last one, the number 7, the last position here, is the session ID variable. That's a really long string, and it gives us information back. If you looked at the first 4 sets of numbers, what do you think that session ID variable probably is? Maybe an IP address? But then what about after 151? What is all that? That's that random stuff at the end, or seemingly random stuff that is not predictable by the adversary, that is created by the system, that represents and tokenizes the username and password of the person. That's what it is. So let's look at this. The domain is stuff. The flags, usually what we're saying is indicating whether all machines within a given domain can access a variable. That piece right there, if you've got a distributed system that you're attacking, if you're attacking a web server with a database server with a bunch of different web servers back there that are all feeding this in, that flag needs to be set to true and give them access so that they can all use it. That's that danger. Now that they can all use it, maybe you can be one of them or pretend to be one of those. The path or URL, usually that's /secure. Is this an SSL communication or not? Now, in this case, we say false. Expiration. How long will it be until this expires? And it's set to 1970. I have no idea why. Then we're going to name the session ID variable. JSession, whatever it is, and then actually have the session ID. So now, look at these for a second. We're going to pause. I'm going to hold off for about 15 seconds. And I want you to look at these. And I want you to look in the column 7 at the end. And I want you to tell me which one of these, from an attacker perspective and from a defender's perspective, that you like. So what do you see in there that looks good to you? When I look at these and I say shorter is better in a lot of cases. Now, it may be that there's obfuscation in this, but shorter is usually better. Okay, so now let's look at a stored URL session ID. Let's look at these and see which one of these we actually like. So I like the fake one. I like the evite state. They're nice and short. I also like that J session ID. That one looks good to me. And why? Well, we'll get into that in a second. Here's also session IDs in hidden fields. Hidden fields are, from a defender standpoint, are very bad, and from an attacker standpoint, are very good. Look, the session ID value is in plain text. Ooh, boy, do I like that. And that's probably pretty predictable. The user account value, again, that looks pretty predictable too. We know the bounds of it. So these hidden fields are nice little tools for us to use, and these happen to be relatively short. So over the next couple of slides, we're going to take an example of brute forcing session IDs from 123 greeting cards, and we're going to do that. So here's greeting cards, and I send out a message. An anonymous admirer has sent you a greeting card, free. To see the greeting card, choose any of the following options which work best for you. Click this link. Now, that link down below is associated with a greeting card that came from somebody and is for me. So look at what we see in front of us with 123 greeting cards, or 123greetings.com. Is there anything in there that you're looking at? Remember, from a defender standpoint, we want randomness. From an attacker standpoint, we want predictableness. How about that? Notice that AD 3072512221 is all the same. The session ID is only random in those 5 digits for right now. And they're not very far apart. They're really only random increments, 16, 18, 20, 22, 24. See another pattern inside of there? What would be the next increment that you would see here? I think that the next session would be 26 and then some 3-digit number. How long does it take to do 26 and 3 random digit numbers, and could you send all of those in as supplied request and intercept? I think it'd be pretty easy to craft that. That would take a script, 15, 20 minutes at the most. So there's lots and lots of predictability here. Good for us as the attackers, bad for the defenders. Okay, so now let's look at another example here. So this is from Computer World, and we look inside of this hacked in the press, and we see at the very bottom, the last line, session ID equals. And we've got a nice short number there. So that's probably, if we could increment that a couple of times, we could see that actually when we incremented from 78 to 79, we could actually get another session ID. Let's look at a cookie example, free server. So the login looks like this really, really long string, but really what happened was they did a base 64 encoding. And what we could do is a base 64 decoding. And you can go to securitystats.com, their tools, base 64 encoding. There's a whole bunch of base 64 encoders or decoders out there. And then what you would do is you would see that the login 123123 with a username of password, all they did was obfuscate here. So every time you find those logins, if you could go search for those logins, every time you find those logins, you could then automate that to do the base 64 decoding, and you would get the username and password. They didn't trade it out for something random, they just hid it. The longer way is to use brute force in every single cookie character combination, and you can still do that, because there are all sorts of tools that will do this for you. Like this tool, Session Brute Forcer. Really elegant tool that will allow us to do this randomization here. You'll notice down in the cookie parameter portion, I know it's kind of hard to see there, you'll see that it's got blocks, and you can say it's between this number and this number, and you can randomize in each one of those sessions, so each one of those sections, so that you can actually make predictability in your cookies that you're offering up from brute forcing. Okay, so here's some URL and cookie for authentication. This is the Session Brute Forcer here. Amazon.com. This one won't work, by the way. That's a really, really long string. Look at the cookie, session ID, and it's got that block of numbers in there. If you're trying to attack one of these organizations, what you want to look for is you want to look for short session IDs. If you have long ones, it's just going to take a long time. You will be eventually be able to brute force it, but then what would happen is probably that session ID would expire, or they would make you re-authenticate in a lot of cases. So that's just one tool, Session Brute Forcer, that will help us get inside. So let's zoom back out again. We've been digging down into the session IDs and the session cookies. What can we look at generically? What can we look at from a design perspective to say, okay, let's prey upon things. Let's work in a particular area. Well, look at the algorithm that they're using. And when we get into the wireless section, realize that they used a great algorithm, RC4, but they weakened it by stripping out a big chunk of the encryption. No form of account lockout. CAPTCHA is not your friend. And for the web, most of the time we don't do account lockout. A short key space. If your session IDs are only 10 characters long, that's very short. We can use brute forcing to get into that. Indefinite expiration on a server. In other words, don't ever let these cookies expire. That's great for e-commerce, and that's great for us as attackers. That's bad for the defenders. Transmitting in the clear. Anything that's sent in the clear or base 64 encoding, as soon as they're doing that, you win. As soon as you see base 64 encoding. And then also insecure retrieval. Change my password kind of stuff makes it really difficult. Okay, so now we need to flip ourselves over and say, okay, what are they doing to stop you from your activities? What kind of resistance can you expect? So from a user perspective, they're going to tell them to log out of all the sessions. They're going to tell them not to use the remember me. Every user uses remember me. I think even I do in a lot of sites. Make sure that you're using SSL. I actually worked with an accountant, and we got rid of the accountant because they said, oh, you can submit your tax returns here. You can upload them to this file loader right here, not using any HTTPS. I changed. Well, the rest of the people at tax season, because it was that time of year, probably didn't care and they just uploaded. Users are being taught to patch and turn on automated patching so that we can't use that, but that doesn't help against the websites themselves. Emails with session IDs are good for us as attackers. They're bad for defenders. They're bad for users. And as soon as they see session IDs, they should drop them. They should say, that username and password, something's inappropriate there. We don't want that to happen. I actually had a security organization send me my session ID with all of my authentication credentials built into it. I have mentioned that security organization throughout these 20 domains here. So know that there's somebody out there that's still doing this. Software vendors, the people who are designing this stuff, they should be using SSL, and that's going to stop us in a lot of cases. They should do the secure field for the cookie. That means that they're putting it inside of SSL. They're going to do automated logout functions so the session doesn't last very long and then to destroy the cookie afterward. Re-authenticate before critical actions like changing passwords, those kinds of things. They should be doing that. They're not. Regenerating the session ID after certain intervals. So now what we're doing is we're randomizing. This generates what's called a race condition. Create booby-trap session IDs. So if there's somebody that's doing brute forcing against you, you look for those incremented session IDs. So if session ID number 1 and session ID number 50, those are valid ones. In between, there's one here that's 25. When somebody puts in that string of 25, it catches them. The intrusion detection system says, that's invalid. Somebody's trying to brute force us. So that's where you want to be careful about what you're submitting, or the intrusion detection is going to catch you. Auto expire session after a certain number of minutes of inactivity. This is auto logging out the user, so therefore that session ID is no longer good. So that means that, again, a race condition. We've got a limited amount of time. We just wait for those sessions and rebuild them. Enforce a number used once on the previous pages. Those nonces, numbers used once, then give them much more randomness in each one of those pages. Cryptographically strong session IDs. I don't know how that works for you. It's all a computing race at that point. Okay, 2 resources for you here on session hijacking. One is from Binghamton EDU and the other one's from me. The Binghamton is very, very specific. It talks about another view of how to teach you session hijacking. Remember, your 2 tools are EtterCap and HPing. If you need a lot more reading on this and you feel that you can go another step further and you want to be good at hijacking, go to the Expanding Security site and go to the readings on CEH-11 session hijacking. It will actually give you a lot of material where you can become great at session hijacking.